A thunderstorm is simultaneously terrifying and awe-inspiring. Nothing in nature demonstrates the devastating effect of static electricity better. It is something we have all experienced. The average lightning bolt has 1 million kilowatts of energy. That's enough to heat the surrounding area to 6 times the temperature of the sun. For all its power, it is simply an exaggerated version of what happens when we do this. Electricity is the flow of charge. When there is build-up charge on a surface, there is instability. The charges want to get off the surface as quickly as possible. The more the charges on a surface, like on a woolen sweater, a comb, or a cloud, the more the charges want to live. The story of electricity is told at the Electrotechnic Gallery of the Visvesvaraya Industrial and Technological Museum, Bangalore.
So how did we get to where we are? What were the milestones in electricity? And how did we begin to understand this mysterious force? Well, it all began in ancient Greece in 600 BC.
Thales was the first person to discover static electricity. He was also the first person to record the magnetic properties of lodestones.
So you see, the discovery of both electricity and magnetism occurred simultaneously. Yet it took almost 2,500 years for them to be united.
Thales of Miletus noticed that when he rubbed a piece of amber, which is a resin, on cloth, it suddenly developed the property that it could attract light objects such as leaves. This is due to static electricity, the buildup of electric charges. What is a charge?
The answer lies in the structure of the atom. Look at everything around you. It is made up of billions and billions of atoms. If we could zoom into an atom, for example in a helium balloon, and ignore the objections of quantum mechanics, it would look something like this.
Does it look familiar? The nucleus, which is in the center of the atom, is orbited by electrons which are assigned on a negative charge. Protons in the nucleus are positive. The other things in the nucleus, the neutrons, have no charge. Electrons are incredibly light, so light that compared to the weight of the neutrons and protons, they are virtually weightless. Because of this, they zoom around the nucleus at fantastic speeds. If one of these electrons somehow leaves the atom, it becomes a moving charge. Protons are too heavy to move. So, if there has to be motion of charge, it has to be because of electrons. As more and more electrons get knocked out of their orbits, they tend to accumulate on the surface of the material to create static electricity. Static charges can be built up by rubbing different materials. For example, rubbing an acrylic rod with a piece of cloth rips the electrons off the cloth, which stay on the surface of the rod. When this is brought near styrofoam balls, it attracts them. If the same experiment is repeated with a PVC rod, the charge built up on the rod would repel the styrofoam balls. The golden rule is, like charges repel and unlike charges attract. If a surface is neutral, it does not mean there is no charge on it. It simply means that the positive and negative charges are equal. If an extra charge, say negative, is brought nearby, it will push away the negative charges and attract the positive charges, leading to a slight positive charge near it. This is induction, and this is what we see with the acrylic rod.
Scientific progress plodded on through the next 2,000 years, and it wasn't until 1600, with the publication of a seminal work on the magnet and magnetic bodies and on the great magnet of the Earth, that William Gilbert ushered in a new age of enlightenment in the subject. He was the first person to use the term electricity, although not in English, to describe the property that amber had. In fact, the word electron is Greek for amber.
Gilbert also studied magnetism extensively and was the first person to postulate the existence of Earth's magnetic field. He did, however, believe that electricity and magnetism were two completely unrelated forces. It wasn't until Ørsted and Maxwell came along 2 centuries later that he was proved wrong. But more on that later. The separation of static charges is most dramatically manifested during a thunderstorm. The great American scientist Benjamin Franklin performed a famous and idiotic experiment to prove that lightning was a form of electricity. During a thunderstorm, he flew a kite which was attached to a key. The rainwater turned the kite string into a conducting material which brought electrons from the sky right up to the key, which then formed sparks near Franklin's hand. Franklin was incredibly lucky not to be killed by the immense power of the lightning bolt.
Franklin was no doubt curious about where the lightning came from. The answer to that question is in the clouds.
Each storm cloud is made up of billions of ice crystals of various sizes. By a complex mechanism, the smaller particles develop a positive charge and by virtue of being lighter, end up at the top of the cloud, creating a charge separation to the negative charges at the bottom of the cloud. The Earth's surface is huge and neutral, so it can be thought of as a vast reserve of both positive and negative charges. The more charge builds up on a cloud, the more it wants to be discharged by reaching the Earth's surface. The charged cloud induces an opposite charge in the ground beneath it. At some point, a path of ions, which are charged atoms, forms from the cloud down to the ground. This path is called a leader and is generally invisible. It takes some time for it to reach the ground. As soon as it reaches the ground, because it is made of ions, it conducts the positive charges from the Earth up to the cloud. This flow of current from the ground upwards is what is seen as lightning. At the museum, lightning is created every day using the exhibit When Lightning Strikes, which takes us through the facts of lightning.
Let us now return to the story of the development of electricity. In 1660, a German Otto von Guericke invented a simple static electricity generator. The first static electricity generator, in fact. Using the principle that friction can rip charges off surfaces and accumulate them there, von Guericke started a revolution that culminated in our ability to generate power on grand scales using electricity. Until now, any attempt at a description of electricity or charged particles focused on static charges.
At the museum, there is an interesting section called the Spark Theatre, which is used to explain static electricity. This section has various interesting exhibits like Van de Graaff generator. The Van de Graaff generator was invented by Robert Van de Graaff in 1931, which produced a huge charge of static electricity. It has a rubber belt which runs over 2 rollers. The belt is driven by an electric motor. One roller is made up of perspex and the other is made up of polythene. When the perspex roller is placed at the base of the generator, the belt running over it becomes negatively charged. The charged part of the belt rises to the polythene roller at the top of the generator, where there is a device that transfers the negative charge to the hollow metal dome. Very high charges can be stored in the dome and released during investigations. This is noticed when a metal sphere is taken near the hollow dome. The charge flows through the air, causing an arc. Faraday's cage is a metallic enclosure that prevents the entry or escape of an electromagnetic field. Michael Faraday, in his work on static electricity, demonstrated that the charge only resided on the exterior of a charged conductor, and exterior charge had no influence on anything enclosed within a conductor. This is because the exterior charge is redistributed and the interior fields are cancelled as per the Faraday's cage principle. Let us see, how does a Faraday cage work? In this picture, an external electrical field is created, marked in blue color in the direction from plus to minus. Immediately after this field is applied, the electrical charges inside the cage walls are rearranged in the way depicted in this image, since opposite electrical charges attract each other. As a result, another electrical field is created, which marked with red color between the cage walls in the opposite direction to the original field and with equal magnitude, and therefore these two fields cancelled and the electrical charge inside the cage remains neutral. The most dramatic application of Faraday cages is lightning safety. If lightning strikes a closed metal aircraft or car, the occupants are safe as long as they are not in electrical contact with the outside metallic surface. The enclosed metallic car or aircraft acts as a Faraday cage and shields the interior from the strong electric field of the lightning strike. The Tesla coil is one of Nikola Tesla's most famous inventions. It is essentially a high-frequency air core transformer. It takes the output from a 230 volts AC source to several kilovolt transformer and driver circuit and steps it up to an extremely high voltage. Large coils have been known to wirelessly light up fluorescent lights up to 50 feet away, and because of the fact that it is an electric field that goes directly into the light and doesn't use the electrodes, even burned out fluorescent lights will glow. The plasma globe is usually a clear glass orb filled with a mixture of various gases, most commonly helium and neon. Placing a hand near the glass alters the high-frequency electric field, causing a single beam to migrate from the inner ball to the point of contact. The beams initially follow the electric field lines of the dipole but move upwards due to convection.
In the 17th century, the English astronomer Stephen Gray was the first person to experiment with moving charges. One person who did get the credit he deserves, and is in fact celebrated to this day as a revolutionary scientist, was Volta, inventor of the battery.
Creating a battery, which is a portable source of energy, Volta found that the largest potential difference was between silver and zinc. We can easily detect a potential difference whose unit, the volt, is named in honor of Volta using zinc and copper electrodes in a conducting solution. This is the first battery ever made and is made using copper and zinc alternating in layers with a conducting liquid called an electrolyte in between. Along with Volta, the Italian physician Luigi Galvani deserves credit for his discovery of bioelectricity. His famous experiment, as described here at the museum, involved frog's legs and a spark. He disagreed publicly with Volta about the nature of the electricity, claiming what he had found was exclusive to animals. Volta, of course, realized that it was the frog's legs that served as a conductor of electricity as well as a detector. It's a peculiar fact that Galvani believed that the electricity that he was dealing with was somehow different from the stuff that Volta was dealing with.
Working with the cell that Volta had just invented, the German physicist George Ohm discovered the direct relationship between current and voltage, a law now known as Ohm's law. The two types of charge were first identified by the French chemist C.F. Dufay. At the time, they were referred to as vitreous and resinous, based on the two types of charge they had. The phrases were later changed by Benjamin Franklin to the terms we use today, positive and negative. In the late 18th century, Charles-Augustin de Coulomb, a French physicist, developed his own apparatus, the torsion balance, to study the distribution of charge on a surface. He developed a mathematical formulation of the now famous inverse square law, which was first hinted at by the English physicist Joseph Priestley. The law now bears Coulomb's name and is one of the most famous in all of physics. The SI unit of charge is called a Coulomb in his honor.
Objects are usually electrically neutral or uncharged. They become electrically charged when one material is rubbed against another. There are two types of charges, namely positive and negative. Gold leaf electroscope is an instrument used to detect the presence and magnitude of electric charge on a body. When you bring the positively charged acrylic rod near the metal plate of the gold leaf electroscope, the leaves deflect, indicating the presence of electric charge.
It's quite amazing how an idea that has eluded man for generations can suddenly become so obvious in the space of a few years. Although it culminated in Maxwell's theoretical and complete unification in 1864, electricity and magnetism were united based on the practical advances of many important scientists in the late 18th and early 19th centuries. We will have to break our chronological look for a little while and focus on a few concurrent developments. Perhaps the greatest English scientist since Newton, Michael Faraday had no formal training as a scientist. He made the acquaintance of chemist Humphrey Davy and became his assistant. An insatiable curiosity and a fortunate job led to some great discoveries in physics and chemistry. Before we look at Faraday's contributions to electromagnetism, let us take a quick look at some of his other discoveries. He is widely praised as being the greatest experimenter in the history of science. This expertise led to discoveries of chemicals like benzene, whose ring structure was elucidated by the French chemist Kekulé after a famously vivid dream. Along with Davy, Faraday made great contributions to the study of electrolysis, the process by which electricity is used to decompose liquids. His legacy is undeniable, and the SI unit of capacitance is called the farad in his honor.
Back to electromagnetism. Faraday's breakthrough came when he wrapped two insulated coils of wire around an iron ring and found that, upon passing a current through one coil, a momentary current was induced in the other coil. This phenomenon is known as mutual induction. In subsequent experiments, he found that if he moved a magnet through a loop of wire, an electric current flowed in the wire. This current also flowed if the loop was moved over a stationary magnet. His demonstrations established that a changing magnetic field produces an electric field. This relation was modeled mathematically by James Clerk Maxwell.
Faraday later used this principle to construct the motor, as demonstrated here. This is a device that turns electrical energy into mechanical motion. An electromagnetic coil is placed between two permanent magnets as shown. The poles of the electromagnet can be reversed as necessary. When like poles come in contact with each other, they repel, causing the magnet to rotate halfway. At that point, the polarity has to be reversed so that the rotation is completed, because the new north pole now attracts the south pole magnet. Notice how tricky it is to actually get a steady rotating motion? In 1820, André-Marie Ampère, a mathematician and physicist from France, laid the foundation for the subject of electrodynamics, as he called it. Ampère's famous demonstration, which linked the effects of magnetism and electricity, centered around wires carrying current. It is a simple experiment to try. Here, we have two sheets of aluminium foil suspended so that they can move freely. Each sheet is attached to a terminal of a DC source. The polarity of the DC source can be changed as necessary. When the current flows in the same direction, the sheets repel, and when the current is in opposite directions, the sheets attract each other. If we had just performed this experiment 200 years ago, we would have been present at the birth of electrodynamics. The law that bears his name deals with calculating magnetic fields created by current flowing in a closed loop. In the same year that Ampere demonstrated his current-carrying wire experiment in France, a Danish physicist named Hans Christian Ørsted showed that a compass needle deflected in the presence of a wire carrying current. This confirmed the suspicions that Ørsted had had for a long time about the relationship between electricity and magnetism, although it took another 40 years for Maxwell to explain theoretically why the forces are linked. James Clerk Maxwell was a Scottish physicist and mathematician who worked at King's College London. His equations, a true poem in physics, unified electricity, magnetism, and optics beyond all doubt in a mathematically sound way. Written in one form, they can be interpreted as a summary of the laws of Gauss, Ampere, and Faraday. Maxwell's unification is generally referred to with respect to electric and magnetic fields, but it should also be remembered that light was incorporated into his theory. This came from a purely mathematical coincidence. The speed at which the waves in an electromagnetic field spread just happened to be the same as the speed of light. This was too much of a coincidence to Maxwell. A few short calculations later, and light was shown to be part of the theory. The result was that any radiation which travels at the speed of light, be it infrared, ultraviolet, X-ray, or even visible light, all belongs to the same spectrum, the electromagnetic spectrum. In Maxwell's own words, from the determination by Kohlrausch and Weber of the numerical relation between the statical and magnetic effects of electricity, I have determined the elasticity of the medium in air, and assuming that it is the same with the luminiferous ether, I have determined the velocity of propagation of transverse vibrations. The result is 193,088 miles per second. Fizeau has determined the velocity of light, 193,118 miles per second, by direct experiment. This coincidence is not merely numerical. In 1879, just 3 years after the invention of one revolutionary device, the telephone, Thomas Edison invented the light bulb, a similarly revolutionary device. Although its working is not based on the unification of electricity and magnetism, its invention came after Maxwell's work. Of course, once electricity and magnetism were seen as one force, their development has been simultaneous. Let us have a look at the incredible impact this unification had. From a purely technological point of view, the last 150 years has seen, by far, the steepest rise in communication technology of any period in history. If we compare technological advances in the 2000 years before Maxwell, as opposed to the 150 years since, the result is obvious. Maxwell's equations changed humanity. In 1911, Onnes discovered the effect of superconductivity, a property of certain materials to lose all resistance to flow of electricity under certain conditions. What talk about modern physics is complete without a mention of Einstein? If not for his remarkable work in space-time geometry and relativity, he would surely be remembered for the contributions he made to quantum mechanics. Indeed, the Nobel Prize was awarded to him not for his most famous work, which was considered to be too controversial at the time, but for his explanation of the photoelectric effect, the basis of the mechanism of the photovoltaic cell, which is the source of electricity derived from the sun.
The establishment of the link between electricity and magnetism had a significant impact on more than just communication technology. Power generation benefited immensely, and in 1902, Asia saw its first ever hydroelectric power station on the banks of the Kaveri River, making Kolar the first place in India and only the second in Asia to have electricity.
The world's first nuclear power plant opened in Sellafield in England in 1956, followed 13 years later by India's first at Tarapur in Maharashtra. Transportation technology too advanced quickly, and by 1969, a train was built that glided effortlessly and with almost no friction along a magnetized track. This train was called a maglev train.
The first decade of the 21st century saw a focused shift from simple energy sources to clean and renewable sources. Vehicles of the future will be powered by fuel cells, not fossil fuels. Fuel cells combine hydrogen and oxygen to produce energy which drives the car, leaving nothing but water vapor as a byproduct.
The next generation of space probes will be powered by highly efficient electric plasma rockets. This is just the beginning. Just as Maxwell could not possibly have known the impact his discovery would have, we too are clueless about what the future holds. We will just have to wait.
Протяжка. Предварительная, промежуточная. Главное, подъем. Принимаем нормально. 10 секунд, полет нормальный. Принимаем вас. Немножечко растут перегрузки. Вибрации, как обычно.